Hello, YouTube. This is Umils03. So for several lessons now, we've been talking about algorithms, and we said that basically Java can sometimes have more than one way to achieve a particular task. And so the first example we saw of that is sorting algorithms. And so for lessons 39, 40, and 41, we were building up this sorting class, and we said that there are basically three familiar methods that we have for sorting elements within a particular array or array list. And we had different examples, and we started out with something simple like an int array. And then we said, well, as long as we have a more generally sortable list or array, then we can figure out a way to sort it. And we said, well, something even as like customized as the person class is sortable, because what person does is it implements the comparable interface. And we said that the comparable interface requires us to supply a compare to method, which accepts an object and returns an integer that somehow represents some representation of comparing the current object to the other objects, which is being passed in as an argument to this function. So after we talked about sorting algorithms, we talked about searching algorithms, and we just have one so far, and we have the linear search. And it's pretty straightforward how it works, right? It doesn't really seem like there's anything too groundbreaking here. But we had different examples of a linear search algorithm. So for example, if we're just going to deal with an array of ints, then we could look for a target value. And so we had an example of a while loop here. And it says that index position is equal to 0. And I'm not going to update the result from -1 to anything other than that, unless at some point the array of index positions, so the elements in the array at that index position that I'm currently at, is equal to the target element that I've been looking for all along. And in that case, I'm going to set found equal to true and result equal to the index position. What I wanted to comment on is there's actually two ways to step out of the while loop or the for loop once you found the value. You could either keep track of a variable and you could just go ahead and change the value once this Boolean becomes true, right? Once you find the value, you say, okay, found equals true, and that would literally prevent you from going through this loop anymore. But I guess an alternative solution here is to do away with the Boolean found variable. You actually wouldn't need that. And then, but what you could do is you could just break out of the loop if at any point the Boolean becomes true. So instead of keeping up with it and just flipping its value like a light switch, you could say, if we ever actually make it to that point, then we could just go ahead and break out of the loop. And this would function in the exact same way, and you would get the exact same output. So you can either use a break statement, or you can keep up with a Boolean that will indicate whether or not you should keep iterating through the loop on account of whether or not you've actually found the value yet, because we want the index position of the first occurrence. And so we just want to stop looking if we get to the index position of the first occurrence. And so you either break out or you switch the Boolean, and so that would prevent you from iterating through the while loop anymore. And then we did the same thing. We did a linear search with an array list of person objects. And we said, well, we can write extremely similar code. The only difference is there's two fundamental differences. I guess, well, sort of two, right? Because one is that the data type is different. So now we're not just talking about ints, we're talking about person objects. And so that would require us to, basically, it would require us to call the getName method, right? Because person objects, we're not searching for a particular person object here, we're searching for a name. So in order to get from a person object to a string, we have to call the getName method, and then we can go ahead and do that comparison. And at the end of the last video, we saw that if we feed in, we had this example, because what happens is we had this example where we were looking in the main method of the searching class, right? And so what happens is we scroll up here, and we said that if you concatenate lowercase kev with in, even though Kevin is in this array list, it's case sensitive. So the only thing, and we saw an index position of -1, which indicates that lowercase Kevin doesn't appear as a name in the array list of person objects. But then if you went ahead and you made a simple adjustment, what I was trying to say and running out of time at the very end, is that if you simply modified your code to say equals ignore case of name, then we know the difference from lessons 5 and 6 between we know the differences between the equals and the ignore case and the equals ignore case methods. So now if you could go ahead and mix it up some more. So you could say KE, concatenated with a V, concatenated with an IN, and now we should be able to return the index position that we're looking for. I mean, we could add P3 twice, right? So now P1 with Kevin is going to exist at index position 1, but at least it'll be able to find it because in the modification, we switched equals to equals ignore case, and now it's no problem to have a lowercase Kevin. What we're going to talk about in this lesson is we're going to talk about another way to search for an element. And with a linear search, the nice thing about it is you don't need a sorted array. You don't need a sorted array list. So if you're just going to step through one element at a time, it's pretty easy. It seems pretty intuitive that you'd be able to start at the beginning of the list and just look at every element one at a time and see, do you end up reaching the target element? Do you ever end up getting a match? And so that's called linear search. But there's also another type of searching algorithm, which we're going to spend the next 14 minutes investigating, and it's called binary search. And the way that binary search works is that it operates on a sorted list or a sorted array. And so we already came up with 3 strategies for sorting an array or sorting an array list. So after having studied bubble sort and insertion sort and selection sort, if you watch those videos, you're at least familiar with those concepts, you should have no problem using the binary search on a sorted array or a sorted array list. So what the binary search does, apparently it's also called logarithmic search, but basically what it does is it keeps essentially dividing the list or the array by 2 each time. And so what you can think about is looking for a word in a dictionary. Let's say you didn't know the definition of the word potato and you just had no idea what that meant. And so you're going to crack open the dictionary, and usually M or N are the letters in the middle. So you flip it open, you hit you hit maize, and you say, oh, I know what maize is. I'm looking for potato. So then at that point, if you see the M, you realize that you haven't flipped far enough into the dictionary. So you would actually basically divide the dictionary by 2, and now you're just looking at M to Z, okay? And then you would basically do another flip in the second half of the dictionary. What's between M and Z? That'd be something like what, S or T or something like that. So you see the S and you say, oh, I went a little too far. I know that P, potato for P for potato is between M and S. And so you've already divided the dictionary into 2, like twice, and then you can see how you're already dealing with a much smaller subset of words to look for, right? You can think about just like flipping through a dictionary, right? That would be an easier way to look for the word potato than to start at the beginning of the dictionary and to perform a linear search. What if you said aardvark, apple, afterwards, right? And then you would just have to search linearly until you get down to P. But there's a lot of words in the English language. So as long as those words are sorted, what we're going to do is we're going to apply a binary search instead of a linear search if we have sorted elements, if we have a list of elements that can be sorted. And we talked about different types of elements that can be sorted. Strings can be sorted according to their length. Person objects can be sorted according to this compare to method. Remember, we said that one person is quote unquote less than another person if the length of the get name method of their name is shorter than the length of the other person's name. And so we already clarified that, and we've been talking about this and describing this multiple times in the previous few videos. But let's go ahead and implement binary search because we're going to operate it on an int array. It might suffice. We might just do it for an int array for this video. But I want you to understand conceptually, at least if we're going to do it for a simple data structure like that, then at least you should really understand what's going on with it. So basically, the way that my binary search method is set up is I actually use this technique called a helper method. And what a helper method does is it essentially is a method that calls another version of a method. So essentially, this is going to be my primary binary search method. It's actually going to be this one that I wrote first. But it's only 1 line long. And so why is this only returning 1 line? So basically what I'm going to do is this binary search is actually going to be performed on an array of doubles. And let's keep that for this example, right? We've already been talking a lot about an array of ints. We'll keep a simple data structure. We don't have to do a binary search on a sorted array list of person objects, but let's do it on a double array just to mix it up and not, be stuck with ints all the time. So here now, instead of having an int target, you'd have a double target if you were looking in a data structure of double expressions, double numbers, right? So we're talking about floating point numbers. And it says if you want to call the binary search, remember it's the same set of parameters as we saw with linear search. It's a static method. It returns an integer index position, and it simply accepts a data structure. It could be an int array, a double array, a string array, a Boolean array, a person array. And then it also accepts a target element, right? And so when we were looking at the person array list, we said that our target element was going to be a name. And the only thing we have to do to get a string out of a person object is called the get name. So that was straightforward enough. But here, this is even easier. So here we're just going to be looking at numbers. And so this array forms a bunch of doubles, which, and so one of them might end up being equal to the value that number has. And so you're going to run binary search on array of number. You're going to pass in the same exact two inputs to this overloaded version. So this one also accepts an array of doubles and a number. It's basically accepts the same inputs, but it also has this left and right thing. So what's going on with that? So when you call binary search for the first time, what it's going to do is it's going to apply this binary search method with a 0 in array.length -1. So you think about index positions, right? You think about an array with 10 elements in it. And basically what this is going to do is the first time you call the binary search on that array with 10 floating point numbers in it, it's just going to basically call this method, but it's going to assign for the first call to this binary search method down here, it's going to make the left variable equal to 0 and the right variable equal to 9. It's just the length of the element, the length of the array -1. You can think of 9 as like the last valid index position, right? If you're thinking about 10 elements, then the valid index positions are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so you're going to say index result equals -1. We're familiar that we typically return -1 if an element is not included in an array or an array list, or a substring is not included in a string. That's pretty default to say -1. And then what you're going to do is you're going to say, well, this argument here is less than or equal to this argument. So certainly you would have a 0 here and a 9 here the first time you call the method, assuming that you're calling it on an array with length 10, right? We would say that left would be 0 and right would be 9. And you have to remember that this array is already sorted, okay? So you have to remember that this array is already sorted. So we know that the element that occupies this index position, the index position 0, is certainly going to be less than the floating point number that occupies index position 9, the right one. And so it's going to say, while left is less than or equal to right, it's going to come up with a midpoint. And that's like what I was talking about with the dictionary, of how you're going to take the average of the beginning and the end of the dictionary, okay? And you're going to look at that middle number, right? So we were looking at the M, but we have to get to P, okay? And so array of mid, right? That would be basically less than the number. If you're thinking about like lexicographically in like a dictionary or something, and you say that the letters later in the alphabet are associated with like bigger numbers, what this would do is when you flip to M, if you're still less than P, if you're still further left than where you need to be, then what this does is it assigns the left endpoint to be the mid endpoint +1. So now, instead of looking at A to Z, you're looking at N to Z, because this Boolean was true here, right? Array of mid is like flipping open the dictionary to an M. It's like the middle letter. And in number, this is like the target. That's what you're looking for. So that would be the P, and that comes later in the dictionary. So you would readjust the left endpoint. So now instead of looking at this dictionary, right, where I guess here was P, M, and this was P, right, you're just going to flip it. And you say, okay, now I get this M here by dividing the left and the right end, by taking the average of the left and right endpoints. And M is still too small. I'm in P. I know I'm in the second half of the dictionary. So I just readjust the left endpoint to now be the mid +1. And now I'm only looking at a dictionary that's half as large. And you can guess that by cutting a dictionary by 2 every time, pretty quickly you're going to converge to the element that you're looking for. It's going to be a hell of a lot faster than trying to baby step through this one element at a time like we did with linear search, right? Apple, aardvark, afterwards. That would be a much poorer way to do this, right? Than to flip, oh, M, I got maze. Okay, I got to keep going. Oh, S, I went too far. Okay, let's go back a little bit, right? And then you're going to converge on that P much more quickly than if you go A, B, C, D, E. And so, right, and then in the opposite case, if array of mid, so, if you flipped to the M, but you were looking for an E, then you would adjust the right endpoint to be mid -1, okay? And then if you land on the number, eventually you're gonna land on the number. Eventually you're just gonna find it, at which point you would set the index result equal to whatever that value of mid is, right? You found it in the middle of the dictionary because you kept dividing by 2 and you kept looking at a smaller and smaller collection of elements. And so eventually, hopefully you're going to converge to this Boolean, right? You're going to be running these Booleans for a lot of times. And then eventually you're going to get to array of mid is equal to number. And then at that point, you would break out of the loop. So I don't know if left is ever going to be larger than right, but it wouldn't matter, right? If you hit the value, you say, I'm not even going to check that Boolean anymore. I'm just going to return the index result. that I found. So now let's go ahead and try this out. So you can hopefully understand the working of a helper method, right? This is, I guess, an example of a helper method, because here you're just going to go ahead and call it on array and number, and you just start out with the maximum endpoints, but then you just keep calling this method. You're going to keep calling this method, the binary search. It's not recursive. You're not calling the method over and over again, but it's going to run this code over and over again as long as left is less than or equal to right, and as long as array of mid is not equal to number, because that's the only other way you'd break out of the loop. So hopefully that's clear, and I know we have about 4 or 5 minutes. I just want to demonstrate the use of the binary search method with you, and it would require a sorted array. And so what we could do, I guess, is we could go and we could take a look at the sorting class, and I don't know if we have right now. We don't have an implementation of a sorting array that accepts an array of doubles and returns the sorted version. So what I'm going to do is I'm just going to assume that we're working with a sorted array. Okay, so here's what I'm trying to say. If you like binary search more than linear search, which you should, you need to use a sorted array. Okay, but for this purpose, since we've already talked about sorting a lot, and I don't conveniently have a method that will sort an array of doubles, even though that's how my binary search method works, it works on an array of doubles, I'm just going to pass in an array of doubles that has already been sorted. But you need to be familiar with practicing on those sorting algorithms and being able to write your own selection sort or insertion sort or bubble sort for that particular data type. So if you wanted to sort doubles, you would know how to do that. You just call one of those three techniques, and then you could call binary search. But I'm just going to give it a sorted array already. So I'm going to say 3.2, 3.5, and it's just going to be an incredibly quick algorithm, right? It's sort of hard to demonstrate the differences between linear search and binary search when we're only dealing with like 10 or 15 values. But I needed to make these sorted, right? But you know, it's hard to compare and contrast these linear search and binary search when you're dealing with such few values, right? Because if you have 8, you can just go 1, 2, 3, 4, 5, 6, 7, 8, right? And then if you were dividing by 2 each time, you'd get somewhere between here, and then you divide by 2 again, right? And it would still take you a few tries to divide it by 2. But once you get to 1 million elements, what do you think is faster, to divide by 2 each time or to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? So you can see how for bigger data structures, you're going to want to prefer binary search. But just for tiny ones, you can just step through it real quick. So this is just going to be an already sorted array. Remember, the binary search requires a sorted array. That's the trade-off. Linear search does not require a sorted array. Binary search is faster. Okay, and so now what you're going to do is you're going to come up with a target value. So you could say double target. Target is equal to, let's do 14.4. Okay, so what index position? If we're applying the binary search, we're going to want to get this. We would basically be hoping to retrieve that value 4 quicker than if we called the linear search method. And like I'm saying, for small arrays, for small array lists, it's really not going to make a tremendous difference. But if you're talking about large data structures, go ahead and sort it in an efficient way, at least with insertion sort, and then you're better off calling the binary search. Okay, so that's essentially what we have going on here. Okay, so then what you would do is you can go ahead and call binary search, and we're just going to want to get that index position. So what you would do is you could say, you could say something like system.out.println of searching dot binary search. Remember, if you're calling a function inside of a class where the function's already defined, you don't have to write the class name. So you could say binary search for a static method. Remember, static method applies to class as a whole, but this is a little bit more formal. So then what you could go ahead and do is you pass in the array, and then you pass in the target value, okay? And then we should be able to retrieve that, right? So we should be able to compile and then run it. And indeed, you get that index position of 4 that we were looking for. And the same thing would have happened if you had tried applying it to the linear search. I don't know if we have a linear search that works with a double array right now. We have a linear search that works with an int array. So you could go ahead and write that. What would you do to make this for a double array? You would actually change absolutely nothing whatsoever. You would just change this to double, right? And then this to a double target. And then now you could go ahead and try the same thing, right? And so, but what I'm saying is that linear search would not perform as well as binary search, especially on a sorted array. But we can make sure that those two results would give the same output. So hopefully the two searching algorithms, they're going to do it in different ways, but they're going to arrive at different results. It's just going to take them different amounts of time to do it. So hopefully that gives you a sense of binary search and just cutting up a set into 2 each time. It's a lot faster than linear search on a sorted list. So that's it for now from UMills 03. Thanks for watching, and please subscribe.